In this video, we're going to be looking at sigma notation. All right. Now, basically, we're going to look at a concise notation for adding a bunch of things together. So we call this summation. So sigma notation is just a way to do summations. And we call it sigma notation because it uses the upper Greek letter sigma, which looks like this. So what is sigma notation? Basically, we're going to say the sum of n terms. So a1, a2, a3, all the way to a sub n is written as the sum. So we use this sigma means the sum of a to the I, the a to the I, or not to the I, a sub I should say, from I equals 1 to n. So this tells us where we're going to start. So I becomes 1, then 2, then 3, all the way till we get to n. So if this were I equals 1 to 5, this would be a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub 5, and we would stop because we got to 5. Now in this case, I is called the index of summation, okay? That's the index of summation. A sub I is just the ith term, and the upper bound and the lower bound are the numbers that are represented here. So 1 is the lower bound, 5 is the upper bound, or in any general case we would say n. So let's give an example here. Our first example, we've got from 1 to 6. So we say, first we say, well, I becomes 1, then I becomes 2, then I becomes 3, then 4, then 5, then 6, and we stop and we just add all these things up together. So 3 plus 3 is 6, plus 4 is 10, 15, 21. That's all there is to it. So we say, okay, what about, this is not just I, this is I plus 1. So if we started I equals 0, 0 plus 1 is 1. So then we go to 1, 1 plus 1 is 2. We go to 2, 2 plus 1 is 3. We go to 3, 3 plus 1 is 4. We go to 4, 4 plus 1 is 5. And we go to 5, 5 plus 1 is 6. And notice we have 21 again. Now here, notice that our index of summation is a j instead of an I. Really doesn't matter. Can be any letter. J equals 3, so we're going to start at 3 and say 3 squared plus, we go up to 4 squared plus 5 squared plus 6 squared plus 7 squared. Right? So this gives us, oh, where's my calculator? We've got 9 plus 16 plus 25 plus 36 plus 49 gives us 135. We've got here, this one looks a little more complicated, right? So we've got 1 over the square root of j, starting at 1. So that's 1 over the square root of 1, plus 1 over the square root of 2, plus 1 over the square root of 3, plus 1 over the square root of 4, plus 1 over the square root of 5. And we stop when j hits 5. Right? And of course, you can just plug this into your calculator and get an approximation, or if you've got a calculator that does nice square roots, one plus 1 over the square root of 2 plus 1 over the square root of 3 plus 1 over square root of 4 plus 1 over square root of 5 equals approximately 3.23167. Okay? Here we've got 1 over n k squared plus 1. So we start at 1 and we go till we get to n. Right? So we've got k is 1, so 1 squared plus 1 is 2 over n, plus when we go to 2 we get 5 over n, plus we go to 3, that's 10 over n, plus all the way to n squared plus 1 over n. Now we can't get an actual number for this because we don't know what n is. But notice that we can just keep plugging ones in until we get to, or not ones, but numbers in until we get to whatever the prescribed n is. Here, we're just given f of x sub I delta x. And this is going to become important later on in this chapter. But what we're going to do here is we're going to say, okay, this is just f of x1 delta x plus f of x2 delta x plus all the way to f of x sub n delta x. Notice the only thing that changes is the I. 1, 2, all the way to n. Okay? Now, notice back in parts A and B, we used the same sum and got, or the same, we got the same sum by using two different notations, right? So, notice we started at 0, here we started at 1, we went to 5, we went to 6, but we still wound up with the exact same thing. So that's kind of an interesting point. Now, here are a couple of properties of sigma notation that are important. The first is basically the constant rule. Okay, if you're multiplying a constant times something, you can pull a constant out because it doesn't change, right? Because this would basically look like, instead of doing Ka1 plus Ka2 plus Ka3, we would just say K times A1 plus A2 plus A3, right? So we're basically saying we can use distribution here, okay? Now this one is the sum of sum or differences. And this, because we're talking about sums, we can easily break these up. Instead of having to do both of them, we could do them as two separate summations, okay? Either plus or minus, depending on whether this is plus or minus. Now, this is going to be a very important thing, and one of the few things that you have to memorize for this section. And these are your summation formulas. So basically, even if we don't know what n is, we can kind of get a formula so we don't have to keep just, putting an indefinite amount of things together. We know that they're eventually going to sum to a very specific term. As long as we know what n is, we can later go back and choose our n. So here we've just got that the sum of a bunch of constants is just c times n. And you can see this is kind of obvious. If we say sum of 1 from I equals 1 to 5, well, when I equals 1, this is just 1. When I equals 2, still just 1. When I equals 3, when I equals 4, and when I equals 5, which is just 5. This could be the same no matter what this is. If this was 2, this would just be 2 plus 2 plus 2 plus 2 plus 2, which is 2 times 5, or 10, right? So this is going to be a really important one. And one you don't really have to memorize. That's just kind of obvious. Now the second one, we're saying that if we sum just I from 1 to n, it's n times n plus 1 divided by 2. If we sum I squared from 1 to n, and this is important that this goes from 1 to n. Can't start at 0, has to start at 1. Can't start at 5, has to start at 1. So this becomes n times n plus 1 times 2n plus 1 over 6. And if we sum I cubed, we get n squared times n plus 1 squared over 4. So let's use this and see kind of when we would use this. So let's evaluate the sum of I plus 1 over n squared from I equals 1 to n for n equals 10, 100, 1,000, even 10,000. Now, because these are really big numbers, there's no way I would just sit out and write that, right? I wouldn't even let n be 10 and write that out. What I can do is I can separate this. So let's start the n squared, since my index of summation is I. N squared is a constant that I can pull out. Okay? Now, I can also break this down into two separate sums. Right? Okay, so this gives me 1 over n squared times, now I have the sum of I from I equals 1 to n. Now I know that's just n times n plus 1 over 2 plus the sum of just 1 from I equals 1 to n is just what, the constant times n, or n. So what I'm going to do is I'm going to go ahead and say, well, this is 1 over n squared. This gives me n squared plus n over 2 plus, I need to make this a common denominator, right? So 2n over 2, so I get 1 over n squared times n squared plus 3n over 2, which is, if I multiply this out, n squared plus 3n over 2n squared, which I can see is going to be n squared over 2n squared plus 3n over 2n squared. If I separated it out like this, and I get 1/2 plus 3 over 2n. So now, regardless of what my n is, this is my formula. So I can just plug each value of n in. So if n equals 10, then this is 1/2 plus 3 over 20, which is, oh, I lost my calculator again, 1/2 plus 3 over 20 is 0.65. And if I let n equals 100, that's 1/2 plus 3 over 200, which gives us 0.515. And if n equals 1,000, you can see this is 1/2 plus 3 over 2,000, which is 0.5015. And then if n equals 10,000, that's just 1/2 plus 3 over 20,000. And that's 0.50015. So, notice all I had to do was evaluate this using my summation formulas, and then I can plug in my n's. So if you have any questions about this, about summations, or about sigma notation, just shoot me a remind or ask a question in class.